In this lecture, you are going to study about full adder. The full adder is nothing but a combinational circuit. Here you are going to understand about the full adder, and you will also learn how to implement the full adder using basic gates, derived gates, and also implement full adder using two half adders. Now before going for implementation, let me tell you what is this full adder. Full adder is, as already told, it's a combinational circuit which adds three inputs. They are three binary digits. It adds three inputs. They are nothing but three binary digits. Three binary digits, and it produces two outputs. So three binary digits as inputs, and it produces two outputs. Okay. The outputs are called as sum and carry. Okay. Now if I want to represent this full adder, so I can represent in this way. So this is the full adder. In short, let me denote that as FA. It has three inputs, one input, two input, and the third one. Let me designate the first input as A, the second input as B, and the third input as C in. So C in is nothing but if you have a carry from the previous addition. Now this is going to give two outputs. Let me call the first output as S and the second output as C out. Here S stands for sum and C out stands for carry out. Now let us see the implementation of full adder. Now to implement full adder, you need first the logical expressions for full adder. Now what logical expressions you need to consider? You need to consider the logical expressions for the outputs sum and carry. Now to find the logical expression, you need to find the sum and carry. Now since full adder has three inputs, you can have 8 different combinations of inputs that can be given to the full adder, and for all these 8 combinations you will be getting sum and carry. So let us construct the truth table which has all possible combination of inputs and all the outputs, that is sum and carry, which we are going to obtain for all the input combinations. And from the truth table we are going to write the logical expressions for sum and carry. Okay. So here I will be constructing the truth table. So it has both inputs and outputs. So I am taking the inputs A, B and C in. Next I am going to take the outputs sum and carry. Okay. So first 3 columns represent the inputs and the last 2 columns represents the outputs. Now as I told you earlier, we have 3 inputs, so we get 8 possible combinations of the inputs. So let us first write what are the combination of inputs. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the last combination is 1, 1, 1. Okay. Now these are the 8 combination of inputs. Now for all these 8 combinations, let us find out the sum and carry. Now for the first combination, sum is 0, carry is also 0. For the second combination 0, 0, 1, the sum is 1, carry is 0. And for the next combination, sum is 1, carry is 0. Here we have 0, 1, 1. So the sum is 0 with the carry 1. Here 1, 0, 0. The sum is 0 with carry 1. 1, 0, 1. 1 plus 0 plus 1. We have sum 0 with carry 1. 1, 1, 0. the sum is 0 with carry 1, and for 1 1 1 the sum is 1 with the carry 1. Now we have constructed the truth table which has all the possible combination of inputs, and for all these combinations what are the outputs you are going to get. Now from this truth table we are going to write the logical expression for sum and carry. Okay, so this is the sum and carry. Here I am calling this carry as carry out because we have one more carry called as carry in. Now let us write the expression. Now to write the expression, first you need to identify for what combination of inputs we are getting a sum which is high. So you have this combination of input for which sum is high. So identify that. Then we have another combination of input for which the sum is high, and here we have another combination of input for which sum is high. So 1 0 0 sum is 1 with a carry 0. So even for this combination. Okay, the next combination for which sum is high is this. Okay, now after identifying all the combinations, okay, so let us write the expression. So here I will write the expression sum is equal to, okay, coming to the first combination, here we have 0 0 1. So I can write that as A bar because that is 0, B bar and C in, plus the next one A bar, B, C in, plus the next combination A, B bar, C in bar, plus the last combination A, B, C. Okay, fine. Now similarly, let us write the expression for carry out also, looking at the truth table. Okay, so carry out. So before writing carry out, I will once again recall sum. S is equal to, so as I wrote, A bar B bar C in plus A bar B C in, A bar plus A B bar, A B bar, C in bar, plus A B C. Okay. Now coming to the carry out. Now as we identified for which combinations of input the sum was high, similarly to find the expression, logical expression for carry out, we have to do the same thing. So let me go back to this truth table. Here once again you have to identify for what combinations of input the carry out was high. Now here let us find out the combinations. So here we have one combination for which the carry is high. This is one, and here we have 3 combinations. Okay, so based on these 4 combinations, let us write the expression for carry out. Okay, so coming to the expression C out. Okay, so the first combination is 0 1 1. So it is A bar B C in, A bar B C in. The second combination is A B bar C in, A B bar C in. The next combination is A B C in bar. The last combination is A B and C. Now we have the logical expressions with us. Now if it is possible to implement with these expressions, you can directly go for the implementation. Otherwise, if you are able to reduce the expression, you can simplify it and use. Okay. Now I think we can reduce the expression. Let us see the reduction. First, I will consider the sum expression and I will see how you can simplify it. Okay. So let me rewrite this A bar B bar C in plus A bar B C in plus A B bar C in bar plus A B C. Okay. Now from the first two elements, I think we can take C in as common. Now to implement this full adder using gates, we have to construct the truth table. So this truth table has all the possible combination of inputs along with their outputs. Now as you all know, full adder has 3 inputs, so we have considered all the possible combinations. The number of possible combinations are 8 in number. So we have considered here the 8 possible combinations. They are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Now for all these 8 combinations, we get the individual outputs. So for the first combination, the outputs are 0, 0. The second combinations, you get sum is 1, carry is 0 because 0 plus 0 plus 1. Next combination is 0 plus 1 plus 0, for which you get sum as 1, carry as 0. Next combination is 0, 1, 1. So 1 plus 1 is 0. So sum is 0, carry is 1. Similarly, the next combination 1, 0, 0. We have sum is 1, carry as 0. The next combination is 1, 0, 1. So 1 plus 0 plus 1, sum is 0, carry is 1. Similarly, you have here 1 plus 1 plus 0. So sum is 0, carry is 1. The last combination is 1 plus 1 plus 1. So here we get sum as 1 and carry also as 1. Now after constructing the truth table, we have to write the logical expression for sum and carry. Now to write the logical expression, first we have to identify in the truth table for what input combination the sum is high. Now you get sum high for 4 input combination. So that I have marked here. You can see for this combination sum is high. For the second combination, this one, the sum is high. And even for this combination, the sum is high. And the last combination, sum is high. Similarly, if you have to write the logical expression for the carry out, the same thing what we adapted for sum. That is, identify the combination for which the carry is high. Now the carry is high for 4 input combinations. Here for 0, 1, 1, the carry is high. 1, 0, 1, the carry is high. Similarly 1, 1, 0, the carry is high. 1, 1, 0, the carry is high. So here we have identified for what possible input combination sum and carry are high. Once we identify this, you can directly go for writing the expression. So here I have written the expression for sum. The first combination was 0, 0, 1. So for which I have written here A bar because the input is 0. Okay. Next B bar because the input is 0. C in because the input is 1. Similarly, the next combination we can write A bar B C in bar. A bar B C in bar. Next, this is 1. So A B bar C in bar. A B bar C in bar. Last combination A B C in. So this is the logical expression for sum. Similarly, we can write the logical expression for carry out also. So here I have written, since from the truth table we identified that for 4 possible combinations of input we got the carry out high. So based on this we have written the expression for carry out here. Now after observing the expression, you can just try out whether these expressions are like you can simplify. If it is possible to simplify, you can simplify and go for implementation. Otherwise, if these expressions cannot be simplified, you can just stop there and you can go for implementation. Now for simplification, I have considered the expression for sum. Okay. Now from this expression, I'll just check whether this can be simplified. Yes. From the first 2 parameters of sum, I have rewritten the expression for sum here. From the first 2 parameters of the sum, I think we can take A bar as common. So if you take A bar as common, so you can see we get B bar C in plus B. If I take B, C in bar. Okay. The second two parameters, I can take A as common. So if I take A as common, I'll be getting B bar C in bar plus B C in. This is actually the XOR operation of B and C, which can be represented as B XOR of C in. Similarly, this is XNOR operation. Okay, so XNOR operation is not of XOR. So I can write this as not of XOR of B and C. B XOR of C whole bar. Now we have S is equal to A bar B XOR of C plus A B XOR of C whole bar. Okay, so once again, if you consider this as one element, then you have A bar. If I call this as X, we have A bar X plus A X bar. Okay, so once again, this is an XOR operation of A and X, where X is B XOR of C in. So with all that, our sum expression gets reduced to A XOR of X, which is nothing but B XOR of C in. So we have simplified the expression for sum. Now using this, you can implement. You can go for the implementation of sum using this expression. Similarly, let me show you the simplification of carry out. So let me write the expression for carry out. Carry out is equal to A bar B C in, A B bar C in, A B bar C in plus A B C in bar plus A B C in. Okay. Now you can simplify this expression. Now I can make the simplified version of carry out by using this rules of simplification. So here I'll employ one rule. So as you already know, A plus A is equal to A. So based on this rule, I'm going to modify the expression C out is equal to A bar B C in. Next, so compared to the first expression, in the second expression you can see with every element I have added A B C in and A B C in. This A B C in was earlier available. So these two A B C in and A B C in I have added, provided the meaning of this expression will not change because A plus A is A. Okay. So now we'll go for simplification. Yes. Now from the first two elements, we can take B C in as common. So I'll take B to C in as common. So if you take B into C in as common, we are left out with A bar plus A. Similarly, the next two elements, we can take A C in as common, A C in. So we will be left out with B bar plus B. Similarly, from the last two, we can take A B as common. So you will be left out with C in bar plus C in. Now once again we will be using the rule here. What is that rule? A plus A bar is 1. Similarly, B plus B bar is 1. The same thing, C in plus C in bar is 1. We have used the rules here. So after using the rules, the C out expression gets reduced to B C in plus A C in plus A B. Or in an order, if I have to write this, I can write this as AB plus BC in plus ACN. So this is our simplified expression for carry out. Now we have the simplified expressions for both sum and carry. So using this, we can go for implementation using gates. So let us go for implementation. So first I'll implement using derived gates. Implementation. Under this, first we'll go for using derived gates. So for implementation, let us recall our expressions for sum and carry. So we had what? Sum is equal to A XOR of B XOR of C in. Okay. Then carry out, we had simplified. So that was A B plus B C in plus A. Okay, so let us implement. So for this, how many inputs you require? We require 3 inputs. So take 3 inputs, A, B and C. Okay, so let us go for implementing sum. For sum, I require A, B and C. So first it is A XOR of B. So I'll take the input A and give it to an XOR gate. So A XOR B. So B, I'll take the input and give it to this XOR gate. So here at the output of XOR gate, I'll be getting A XOR of B. Now this has to be XORed with C in. So I'll be taking another XOR gate. Okay. So one of the input for that XOR gate is this A XOR of B, and the next input is coming from C in. So here we'll be getting A XOR of B XOR of C in, which is nothing but our sum. Okay. Similarly, we'll go for the carry. Now for carry, we have the expression AB plus BC in plus AC in. So what gate is this? This is AND gate. AB is an AND gate, BC we have to use an AND gate, AC we have to use an AND gate. So after this combination has to be ORed. Okay. So let me go for the first one, AB. So pass A and B through an AND gate. So here I will be getting AB. Next pass B and C through another AND gate, B and C in. So we will be getting B, C in. Next pass A into C in through another AND gate, A and C in. Okay. So we got AB, BC in, AC in. Next, these products are to be ORed. Product in the sense, the output of these 3 AND gates, we have to OR it. So what I will do? First pass these 2 through an OR gate. Okay. Next, take this input and output of the first OR gate and give it to another OR gate. This will be your carry out. So this is the implementation of full adder using derived gates. So here we will be getting AB plus BC in. Now this input and AC in input is passed through another OR gate to get the carry out. So you can see this is a full adder. So whatever I am blocking, so this is a full adder, for which we are providing A, B, C, which are the inputs. So based on this logical circuit, and for different combinations of A, B and C, you will be getting the outputs S and C out. Now similarly, let us see the implementation of the full adder using basic gates. So what are the basic gates? AND gate, OR gate and NOT gate. So this implementation was using derived gates. So let us see the implementation using basic gates. Now once again, since we are going for implementation using basic gates, we need the logical expression. Now here we have to consider the basic expression without simplification, because once you simplify, you are getting the usage of derived gates. So drop that and we will go for the basic expression. So what is the basic expression for sum? Sum was equal to A bar, B bar, C in plus A bar, B, C in bar plus A, B bar, C in bar plus A, B, C. Okay. So without simplification, because if you consider the simplified one, we have to use the derived gates. So basic sum expression I have taken, and I will also consider the expression for carry out. So what is the expression for carry out? Simplified one. We can go for the simplified one because they are using just AND gates and OR gates without derived gates. So I will go for it. AB plus BC in plus AC in. Okay. So let us implement this. So we have three inputs. Take the three inputs A, B and C in. Now as you can see the expression, we have A bar, B bar, C in bar. This A bar, B bar and C in bar is got from A after introducing a NOT gate in between. So this is A. Through this line you will be getting A. Here you will be getting B and here you will be getting C. Okay. So since we need A bar, you can pass A through a NOT gate to get A bar. So this line is for A bar. And similarly, here you can pass B through a NOT gate to get B bar. And here you can pass C in through a NOT gate to get C in bar. Okay. For the sum we need 4 terms, A bar, B bar, C in. So I will take A bar from here, B bar from here and C in, which is C in. So these are given to an AND gate. Yes. Similarly, A bar for the next combination. A bar, B, so this is B and C in bar. Here we get C in bar. Next A, B bar, C in bar. So here we have A, B bar. So here I will be getting B bar, C in bar. So C in bar is got here. Okay. Next is A, B, C. So where we have A, this is A, this is B and this is C. Now what you can do, you can pass the first two outputs of AND gate to one OR gate, or pass the outputs of these two AND gates to OR gate, and those two OR gates you can combine. Or if you have the 4 input OR gate. So directly I can go for an OR gate with 4 inputs. So all the 4 I can give here, 1, 2, 3 and 4. So all are OR to get the final output sum. Now the carry implementation is same as the above implementation what I showed for derived gates. So there is nothing change here. So you can just take A, B, C in. So here you can take A, B and C in, and you can combine A, B, give A, B to an AND gate, B, C in to an AND gate, A, C in to an AND gate, and give all the outputs of AND gate to OR gate, because these two are OR, to get the C out. Okay. Similarly, you can find out the implementation of carry out. So this was about the implementation of full adder using derived gates, using basic gates, and at last we have one more thing, that is implementation of full adder using 2 half adders. So let us see that. So implementation using 2 half adders. Using 2 half adders. Okay. Now once again, if you go for any implementation, first we should see that we have the logical expression for sum and carry. Yes, already we have the logical expression. So I'll write the logical expression for sum. So what was the expression we got? Simplified one, A XOR of B XOR of C. But when you are implementing the half adder, when you are implementing full adder using 2 half adders, the simplified version of C out cannot be used. So here we are going to write the C out expression in a different way in order to suit the implementation of full adder using 2 half adders. So let me just rewrite this expression for C out and simplify in another way. So I'll just write the expression for C out. So we can just recall, it was A bar B C in plus A B bar C in plus A B C in bar plus A B C in. So I am just rewriting the expression for C in. So here as we did using the rule A plus A is equal to A, so we can't use that here. We are going to simplify directly. So how can you simplify? So looking at the expression, you can see that the last 2 terms I can take AB as common. So we will be getting C in bar plus C in. The first 2 terms, what can be common? C in is common. You can see here C in is common. So if I take C in as common, you will be getting A bar B plus A B bar. Okay. Now one of the rules says, logical rule, C in plus C in bar is 1. So here I will be getting AB. Here we have C out is equal to C in. What is this? A bar B plus A B bar. It is nothing but A XOR of B. So this is our C out expression which can be used for this implementation. So just make a note of it. S is equal to A XOR of B XOR of C, and C out is equal to AB plus C in into A XOR of B. Now using these two, we are going to implement full adder using 2 half adders. Let me write for our reference. S is equal to A XOR of B XOR of C, and C out is equal to AB plus C in into XOR of A and B. Okay. Now let us implement this full adder using two half adders. Now you all know half adder is a combinational circuit which accepts two input and it provides two outputs, sum and carry. Okay, so if I indicate the inputs of half adder as A and B, your sum will be XOR operation of A and B and carry is AND operation of AB. This is how your half adder works. It adds two binary digits producing two outputs, sum and carry, where sum is got by the XOR operation of A and B, while the carry is got by ANDing the inputs A and B. So using this half adder, we are going to implement the full adder. Okay. Now for the full adder, we need three binary digits. So let us see how it can be done. Okay. So I'll be considering the three inputs A, B and C in. Okay. Now we need to implement this using half adder, right? So first let me consider the half adder. So this is one half adder and I am going to give A and B as inputs. Now as I told there, half adder gives S and C. S is A XOR B and C is AB. So same thing here, I am going to get A XOR of B as one output and here I am going to get AB as another output. But actually, what is the sum output of full adder? It is A XOR of B XOR of C in. But here we have only got A XOR of B. So I need an other element also C in. So for that I am going to pass this through an other half adder. So one of the input to this half adder is A XOR B and the other input to that half adder will be this C in. Now this is an other half adder. So as per the rule of half adder, we get S which is A XOR of B and C which is AB. So this half adder gives me, A XOR of B, which is another input to the second half adder. This I'll call it as half adder 1 and half adder 2. So the other input is C in. So I'll be getting here C in. So this is the sum of the full adder. A XOR of B XOR of C in. Next, what is the C out? C out is AB plus C in into A XOR of B. So as per the principle of half adder, the sum is got. What about carry? Carry is nothing but AND of the inputs. Okay. So what are the inputs of the second half adder? One of the input is A XOR B and the second input is C in. So we are going to get the AND of this. What is the AND of this? C in AND of A XOR of B. But still we have not completed the implementation of C out. So for C out, I need another term AB also. So where do you get that AB from? Here. So we have this AB here. So take this AB. Now we have C in AND of A XOR B and here I have AB. So AB and this input you have to pass through an OR gate to get C out. So these two I am going to pass through an OR gate. So this is your OR gate. So here I am going to get C out. So you can see here we have implemented the full adder using two half adders. So here I have just shown you the block diagram. So I have shown you as a block diagram how to implement the full adder using half adders. So you can go for the logic structure also. So what is that logic structure? What is half adder composed of? Two inputs and two outputs. This first output is A XOR of B. So to get A XOR of B, you can pass these two through an XOR gate. A and B. Okay. And what is the second output? AB and. So here you can have a AND gate whose inputs are, one is this A, from here I am getting A, and this is B, and this is your carry. So first one what I showed was block diagram. The same block I am replacing by the logical diagram where this is implemented using derived gates. Similarly, this half adder also, A XOR of B XOR. So already we have A XOR of B. So I can write an XOR gate with one input, and this is the second input. And similarly for carry is nothing but AND of the inputs, right? So I will write a AND gate here. One of the input is this. So pass this, and this is our second input. And output of this AND gate is this. So we can modify the block using the gates also. So this is the complete implementation of full adder using half adder. So in this session you are able to understand what is the full adder. Full adder is nothing but a combinational circuit which accepts 3 binary digits and gives us 2 outputs. One is termed as sum and other is termed as carry out. And you have also understood how to implement this full adder using derived gates, using basic gates, and also how to implement full adder using 2 half adders.